Welcome, everyone, to the first morning of the Cooperative AI Summer School 2025. We're going to jump straight into it, so with a talk from Vince, and then I'll give some slightly more kind of intro remarks and kind of context afterwards, just so Vince can get to a call. So without further ado, Vincent Conitzer is Professor of Computer Science with affiliate and courtesy appointments in machine learning and philosophy and the Tepper School of Business, all at Carnegie Mellon University, CMU, where he directs the Foundations of Cooperative AI Lab, which is focal. He's also head of technical AI engagement at the Institute for Ethics in AI, which is at the University of Oxford, as well as Professor of Computer Science and Philosophy there too. Previously to joining CMU, Vince was the Kimberly J. Jenkins Distinguished University Professor of New Technologies and Professor of Computer Science, Professor of Economics, and Professor of Philosophy, triple threat, at Duke University. He received PhD in 2006 and his master's in 2003 at CMU, where he now resides, and an AB degree in applied mathematics from Harvard in 2001. And as well as all of those many, many things, Vince is also an advisor to the Cooperative AI Foundation and has been right there at the beginning. And so, yeah, gives me great pleasure to introduce Vince to kick off the summer school. Thanks, Vince.
Thank you. I'm really excited to see all of you. You will be the future of cooperative AI. And I think it's really a good field to be in, right? It's a new field. And that means there's still a lot to be determined. A lot is still open. We had the retreat, the Cooperative AI retreat, the last few days. I will say that this bell that Lewis uses has properly conditioned me at this point. So it's not one of those fields that is already well established and where the only problems that are remaining are either the ones that are impossibly hard or just not very interesting, or both. And instead, we really still get to create the field, right? I think that's a great opportunity as an early career researcher. Now, it can also be somewhat frustrating at times because we don't have everything worked out. We don't have all the formalisms and we don't exactly know what are the key problems that we want to. We have a good general idea, but we're still figuring it out, right? And I think we experienced this at the retreat as well. We're still figuring out. What are we trying, what are kind of our key problems that we're trying to solve? We have some idea of what they are. How should we unify all this? Also, we're actually concerned with doing a good thing for the world, right? And so sometimes we also try to check ourselves, right? That we say, well, does this help with cooperation or does it help with undesirable forms of collusion, right? And so we have that challenge there as well. So, in that sense, the field is still a little bit nebulous, but I'm hoping that all of you will help give it the structure to make it a proper and good for the world field. That said, I'll try to get as much across to you today as I can. As you can see from the slide, so as Lewis said, I direct the Foundations of Cooperative AI Lab at CMU, so hopefully very much in line with cooperative AI. And I've been doing that since 2022, so we've had a few years of this now. See a couple of other resources here. By the way, I'll make all the slides available. Many of the things in the slides are actually links if you want to learn more. We have a vision paper from a few years ago together with Casper Oesterheld, who is also here in general. I don't think he's here in the room just yet. We just gave a tutorial at AMAS. That is kind of what I started from with this lecture here, but was a little bit longer. And in fact, we taught a whole course on this in the spring at CMU. So all that means that I have way more slides than I have time for. I'm going to judiciously, hopefully, try to skip slides as that makes sense. But I actually want to keep it interactive, so I'd be very happy to take questions during, if something comes to mind, if something is really unclear, or please feel free to raise your hand and we'll go on a little bit of a detour. It's not important that I get through all my slides. You may notice we have the branding down pretty well. It's all Foundations of Cooperative AI. Again, I think the word foundations here also reflects that we're interested in the foundations. That's maybe putting things a little bit more on the theory side. And maybe in some of the other talks later, you'll see a little bit more experiments and so on. But here we're mostly trying to get clear on what we're doing. You will notice that the title today is a little bit different, right? This "and frontiers" got in there, foundations and frontiers of cooperative AI. That suggestion was from Claude to add that by way of Cecilia. Now, Cecilia, I don't know what prompt you used, but I see that as a bit of a challenge, whether it's coming from Claude or from Cecilia, to really give you the latest. And so I will do that as well. I'll give you a position paper that we just released a few days ago. So cooperative AI, what is it about? Well, we're seeing AI being deployed in practice more and more, right? And as it's getting deployed in more and more places, it stands to reason that multiple AI systems will start to run into each other in the real world as well. Right? When you have systems interacting in that way, sometimes the outcomes of that interaction can be very surprising. They may not be what the designers intended. Sometimes surprising is not particularly bad, but sometimes it can also be quite a horrific outcome somehow. Again, if it's something that we weren't expecting, maybe something much worse happens than we expected. Especially in our lab, we think a lot about one way in which this might happen is that as these systems become more advanced and more agentic, then a lot of these unexpected interactions might take more the form of something like a tragedy of the commons. If you're not familiar with the tragedy of the commons yet, we'll see that in just a little bit. But the idea of it is that sometimes when multiple entities each pursue their own incentives, this somehow leads you into some spiral that things get much worse for everybody involved. Right? This is kind of one of the main lessons of game theory. And this is the kind of thing that also we hope to prevent. And so we're going to think about methods to prevent those bad spirals of selfish interaction. And we're going to think about those sometimes in ways that they apply to human beings as well, but also sometimes in ways that maybe don't really make sense for human beings or human institutions, but actually do make sense in the context of AI. So I hope to show you some of that today. And you can see here the outline is in line with that. I'm going to motivate things a little bit, give you the landscape. I'll give you a little bit of a game theory background. How many of you have some game theory background? Okay. Good, good. Okay, so I can go fairly quickly through that. Then I'll talk a little bit about approaches for cooperation that are natural for human beings. This is, for example, the Folk theorem in game theory, if you already know that. But we'll go over that as well. And then I'll talk about some things that don't really seem to make sense for human beings, but that maybe also give you a kind of Folk theorem for AI agents. Good. Let's go to some examples of unusual interactions. Here's one. So this is on Amazon. So at some point, this book, The Making of a Fly, The Genetics of Animal Design, was for sale on Amazon. And there were two sellers. Sorry, the image is a little bit low resolution, but you can see here that this book is currently selling for about $2 million. Okay? And two sellers, they each sell it for about $2 million. I'm sure it's a wonderful book, but there doesn't seem to be any reason that this book ought to be selling for $2 million. In fact, the used copy is quite reasonable here at $35. So these two sellers, Profnath and Bordybook, how did it come to be that they had such high prices for this book? And the reason is that these prices were being set algorithmically. I don't know if it deserves to be called AI, but somebody figured out at some point what was going on. It was actually a very simple update where you can, and if you can read it, it's a little small, but so what Profnath, its algorithm was look at the price of the competitor, I think it's on a daily basis, look at the price of the competitor and undercut it, right? So multiply it by 0.998 to be just a little bit cheaper. Okay? It's really, really a little bit cheaper. Okay, but interestingly, the other seller, Bordybook, had a different strategy. Bordybook's strategy is take the other seller's price and multiply it by 1.27. Why? I don't know. Maybe Bordybook thought this would make me appear to be the higher quality seller, or maybe Bordybook never owned the book in the first place and was just planning to buy it from the other and take the markup. Who knows? But you can see what the result of this is, right? Because the first ratio is very close to 1. The second one is a little further away from 1. You're going to get this exponential price increase. And in fact, at the top here, you can see it went up to $24 million. And then somebody wrote an article, I think at some point, it disappeared. Okay. I think somewhat funny example. Presumably, not much harm done. Maybe somebody wanted to buy the book and couldn't, or had to buy the used version. Okay. But it is an example of unexpected interaction, right? Presumably, neither one of these sellers had intended or even conceived of this going to happen. Let's look at a little bit more serious example, the flash crash. In 2010, there was something known in the financial markets as the flash crash, where suddenly the market took a dive. Now, sometimes the market takes a dive due to fundamental reasons, right? Maybe war breaks out somewhere and the market takes a dive. Now, that actually reflects something fundamental in the world. Here, that did not seem to be the case. The market was just going up. I think there's been a lot of research on what triggered this and various kinds of behavior involved. But one of the things that played a big role in this was high-frequency traders, meaning algorithmic trading. Somehow, some events induced this behavior that these algorithms would buy things and then not want them and say, I'm going to sell it and push it off. They called it the hot potato effect. And that caused prices to plummet. A stop was put to it at some point, and eventually the market recovered. So again, and now in this case, probably some people made a lot of money, some people lost a lot of money, but the world recovered. Okay? But this is an interesting domain. I think finance is a very interesting domain for us in cooperative AI. You should also talk with Mike Wellman there in the back if you're interested in finance. But it is an environment where we already have algorithms really interacting with each other in a pretty open-ended way that ties to the rest of the world. So in some ways, it's maybe a preview for what is to come in the rest of the world, right? Because as AI gets deployed further and further in our world, it stands to reason we're going to see this in other contexts as well, right? What if something like this happens with agents that are managing the electrical grid, or in cybersecurity, or cyber warfare, maybe even kinetic warfare? Right? Here's a perhaps somewhat disconcerting demo of this is kinetic warfare, right? And even more broadly, AI agents are becoming more and more general purpose, right? So they will be acting in the world in general, in the broad open world, as opposed to in a restricted domain like a financial market. Of course, that too has implications on the rest of the world. But as they work in more and more open-ended domains, at some point maybe we get weird interactions that aren't even limited to a single domain. So how do we think about those issues, and how do we make sure things don't go poorly? We're already seeing these kind of papers being written. So this is about, this is not real. This is just a paper where somebody did a simulation of, as it says, 8 autonomous nation agents based on language models that are going to engage in diplomacy with each other. And then the paper measures, well, how often do the different models actually go nuclear on each other versus de-escalate and so on. Always interesting, like, what should you take away from a language model experiment? I'm sure we'll talk more about that during the summer school. But this is a kind of paper we're already starting to see. Again, as you will hear much more about, there are various thought pieces. Most recently, led by Lewis, there's the multi-agent risk report from the Cooperative AI Foundation. And there's also the one that I already pointed out that's a little bit more on the theory and foundation side from our lab from a few years ago. Again, happy to make the slides available. All these things are links as well. So let's think clearly about what could be going wrong. One thing that could be going wrong is that systems are just actually not very capable or very intelligent. Right? You might argue that's kind of what's going on with the bots on Amazon. Those are not very intelligent. They're just multiplying by some number. And you might argue, well, if only they were smarter, they wouldn't actually do this kind of silly thing. Right? I think that's a good point. Sometimes people say, OK, well, that's fine. But at least if the AI is not that capable anyway, then we don't have to worry too much about it because it won't really take over resources and so on. I'm not completely convinced by that argument either. Right? It could be that AI is very good in some directions but has some weak spots. Right? I think to some extent this is true for language models today, that they're remarkably capable a lot of the time, and some of the time they just go completely wildly off the road. And I think that can still be very dangerous as well. Another problem is that the systems are not sufficiently aligned with what we really want them to do. We try to express what we want them to do, but we actually make some mistakes in that, and consequently they end up doing something, again, that we didn't expect. But I want to focus mostly on the game theoretic issues between multiple systems. So I'm thinking here mostly about systems that are capable and do capably pursue their own objectives. And moreover, it's not even that we got the objective that wrong, that the AI systems actually are roughly doing what we wanted them to do. And yet, due to these interactions, we actually get an effect that is not what we wanted at all. Now, how should we think about agents? I like this. So here we have a story of two self-driving cars. The orange one is coming up behind the green one. And let's say these self-driving cars can send messages to each other. So the orange car says, hey, if I tailgate you, meaning if I start driving very close behind you, will your occupant take over control and pull over to the side? Now you have to understand, if you're a self-driving car, this is a total loss of face. So this is a scary scenario. And so the green car gets a little nervous. Well, what makes you think I would tell you? And the orange car says, you're nervous. You just told me. Just get out of the way. And the green car says, you're bluffing. The orange says, maybe. Are you willing to take the chance? OK. Some of you are smiling. And that's kind of the point, right? This seems silly as a way of describing how self-driving cars would behave, right? We don't actually really expect self-driving cars to behave in this kind of way. But why is that, right? And I would say, in general, in the AI community, we've actually very long thought about this design of agents as a goal of the field, right? Now we hear all these things about agentic LLMs, and to some extent that is new, right? Making the language models agentic is new, but the idea of having agents in AI is a very old idea and has often been kind of a landmark, a guiding post for the field. So let's look at what that typically looks like. So here is, I think from an older edition of Russell and Norvig. I think Stuart has been giving this a lot of thought since. But this is kind of the typical picture that you would see in an AI textbook as to how we think about the design of AI agents. There are multiple figures like this. I picked one, right? So the idea is we have this agent, which is this clear, well-delimited, modular entity in the world that interacts with some kind of environment, right? Could be the big open world, but it could also be a limited environment, like finance or a robotic soccer game or something like that. It has sensors to perceive the environment in some way. It has some model of what the world is like, the state of the world. It also has some model of how the world evolves, including in response to its own actions. And given that model, it now can, in combination with some kind of utility function, or sometimes called maybe preferences, an objective, goals, right? But something that it's aiming for in the world. Because it has something it's aiming for in the world, it can now actually decide what actions to take. That's going to lead it to take an action through its effectors or actuators, something that gives it some control over the environment. Okay, that's your typical picture. And there's always this question, where does utility come from? And again, historically, people have often thought, well, somebody from the outside will tell us what the objective is, right? Our job in AI, this is the sort of traditional view, our job is to come up with the algorithms that will make that work well. We will then have a product, we'll just hand it off with a little blank spot for the objective function that somebody wants to give it. Now that second part, I think the community has by now realized is not very realistic or desirable. First of all, practically, in most cases, you can't actually expect the customer to just fill in that one line of code that is the objective function. But also that's where we have a lot of concerns that it's maybe hard to really, especially in sort of broad open-ended domains, to really express what it is that we want the system to do. This is sometimes called the alignment problem. I'll have a slide on that. But I also want to draw attention to the other part of the image, that everything here is so clean and modular. Right, that each agent is really this whole separate thing. And I think that, too, is a very anthropomorphic way of thinking. And I would say real AI these days is not actually quite like that. So to illustrate that, let's take the example of an AI assistant. Right? That's one kind of agent. And that, too, has long been a dream of the AI field. You can find very early references about the idea of creating AI assistants. To some extent, we really have these assistants now on our phones. Right? So let me focus on Siri. Not for any particular reason. Siri is well known. So Siri, right? The one assistant that we have on our phones. I asked Google, how many people use Siri? And AI Overview jumped in and said 500 million users. Okay? Let's take that as a fact. I actually looked at the sources, so it seems like that's a fairly agreed upon number. In general, by the way, don't always trust AI Overview. Here's a nice example from my student, Eamon Burker, who at some point was applying for a visa. And on the visa application, it had this question that he wasn't quite sure what this meant, like what is an IRCC authorized panel physician? And as one does, he just took the whole question and copied it and put it straight into Google to see what would come up, because presumably somebody else had this issue. Helpfully, AI Overview jumped in and said, yes, I have had a medical exam performed. So definitely still has its downsides. That said, the 500 million I think we can take as given. Now I want to do a poll, and let's see how it goes, because I want you to think about, take all of Siri or Siris, like everything related to Siri in the world. Siri running on everybody's phones, but also on servers, and everything that's part of Siri somehow, right? I want to ask you, how many agents is all that, right? Does it kind of make sense what I'm talking about? Like everything that Siri consists of as it's used in the world. So I'll ask you to vote by show of hands, but I'll first read through the options. So one option is 500 million, or however many users there really are, as we just saw. Another option is 1. Like the whole thing is just one giant agent. Another option is 0. It's not even an agent. Okay? Another option is some other concrete number. Maybe you think it's like the number of servers, or maybe you have some other idea. Then the option is like this whole question doesn't make sense, isn't well specified. And finally, just to make sure everybody will raise their hand at some point, I'll give you the option of saying you're not willing to make a choice without giving this further thought. If you say one of the earlier ones, I won't forever commit you to that either. But OK, makes sense? OK, so everybody should raise their hand for something. OK, who says 500 million agents? OK, good. Who says 1 agent? Who says 0 agents? Okay, got a 0 here. Who says some other specific number? Okay, quite a few. We'll talk afterwards what the number is. Who says this question makes no sense? Okay, quite a few. Who wants more time? Okay, so we got a pretty decent split, right? I think we got relatively few zeros in this particular audience. But I've done this a few times now, and usually it's actually pretty even split, I would say, right? Including at the multi-agent system. I feel like at the multi-agent systems conference we got a few more zeros, but this is pretty typical. Like people don't agree on the answer to this question, right? And so this, I think, is important, that the way that agents, AI agents, may come into the world may not really look like the biological agents that we typically think about. OK. Again, this question of figuring out what the utility function should be has received a lot of attention in a lot of different contexts. I think sort of very narrow interpretations of really trying to figure out the objective function in a particular piece of code, to, I would say, broader efforts at the same issue that, well, maybe in the context of ethics or regulation, what kind of conditions should we put on AI that's deployed into the world? But a lot of that I see as related to each other. But I want to focus more on cases where we've gotten the alignment pretty much right on individual agents, but we get these bad dynamics happening between them. So let's look at a particular example. So let's say we have 2 agents that together are providing us with some kind of service. Okay? And we've trained those 2 agents, and each of those has to choose a quality Q sub I, where I is the agent, with which to provide that service. The overall quality of the final product or service that they produce is the lower of those 2 numbers, right? The quality is determined by the weaker part. And we've gotten the agents to care primarily about overall quality, which is what we care about. We as humanity, let's say, we care about the quality of the service. We've trained the agents, and we've gotten it basically right, but it's still slightly off. Somehow, what has emerged is a very slight incentive for each agent to be the lower one of the 2, right? Maybe they've learned that if you're the lower one, you're going to get some special attention because that's the one that we want to fix up. That would be one reason. Okay. Here is the game for that. Right. So this is how we typically draw what we call a normal form game, where one player and one of the agents. Right. So now we as humanity are no longer a player in this game. We've handed it off, and we have these two agents that each have to choose a quality number. It's maybe a little bit hard to see, but so here it says 190. I've discretized it in tens. Okay, and now in each entry, you can see the utilities of the two players. For example, if the row player, the first player, chooses 80, and the second player chooses 100, then the quality of that will be 80, which is the lower of the two numbers. But the first agent gets a bonus of 22 for being the lower one. Okay, I've set it to 22 here. You can make that as low as you want if you discretize it finer. Okay, and that's how all these numbers are determined. Okay. Now the agents are going to play this game. But first I want to notice a few things about this game. First of all, within every entry, the numbers are pretty close to each other. Not super close, like 22 apart. I can make that go down as far as you want by making the game bigger. But here, so they're always within 22, so not too far apart from each other. Also, all the good outcomes live over here in the top left corner. Right? They both pick a high number. That's what we wanted. Right? And again, also here, they're also well aligned with our utility as humanity. Even though we're not listed as a player in this game, we are the lower number of these two. What happens in equilibrium of this game? So it turns out this game has only one equilibrium, and it is here. Okay, so they will converge over here. And this is pretty robust in the sense, by the way, this game is basically what's known as the traveler's dilemma in the literature, if you know that. That means that any kind of algorithm that you come out, let's say you take some reinforcement learning algorithm that tries to maximize the agent's own utility, right? That's important, right? So the only thing I'm going to assume here is that the agents only really care about their own utility. Right? That's what it means to be utility. That's what you want to maximize. As long as they do that, they will end up over here, right? Because they will always learn it's a little bit better to undercut the other, but then you will be undercut, right? So the dynamics will generally take you all the way down here. In spite of everything else seems like it's pointing in the right direction, it's well aligned, there are good outcomes up here that are good for everybody, and yet we fall all the way down there. Now this, in some sense, is kind of the typical lesson of game theory. Here's the prisoner's dilemma. Since most of you have seen game theory before, let me go through that. I won't go through the whole story. I'll give you a different story in a second. But the typical game theory example is the prisoner's dilemma, where two prisoners have the choice either to confess or not to confess, or often, as we say, to cooperate with the other prisoner, or to defect on the other prisoner, right? And then the lesson is that even though they could both be pretty well off by not confessing, they each individually have an incentive to confess. Because if I'm thinking from the perspective of the row player, you would think, okay, well, if I confess when the other one confesses, it's better than if I don't confess in that case, right? Holding fixed that the other player confesses, I would rather confess too and go to prison a little bit less long. Whereas if the other one doesn't confess, I can take advantage of that by confessing, right? Either way, I'm better off holding fixed what the other player is doing. Either way, I'm better off confessing than not confessing. So they both end up confessing, and they both go to jail. Now, sometimes this sounds nice, right? We got the prisoners to go to jail, good. But in most contexts in the world where this happens, it actually isn't a good thing. So here's, I think, an example that does reflect something about the world. Should I buy an SUV? An SUV being a large car that uses a lot of gas versus a smaller car. And let's say that the cost of the vehicle, including the cost of gas, is 5 for the large car and 3 for the small car. Let's also assume here that the agents that we have in mind, the people that are buying these cars, actually they don't need a larger car, right? I have 3 children. We need a somewhat larger car. But in this case, let's say, for these agents, either car is equally comfortable. But there's one more cost that we have to take into account, which is that maybe one day you get into an accident with another vehicle somewhere. Right? It's impossible today to have some kind of agreement with that person because you don't know who it is. And now, just by basic mechanics, larger vehicles, holding everything else equal, tend to fare better in crashes than smaller vehicles, right? And so let's say that the cost that you incur as a result of being in an accident depends on the vehicle that you drive as well as the vehicle that the other person drives. If you drive the same size car, you both have a cost of 5. But if you drive the smaller car in a collision with the larger car, then you do much worse and the other one does better. Okay? You add up all these costs, and what happens? Again, there is, because we assumed here that there is no inherent benefit to having a larger car besides this accident, everybody would be better off if everybody got a small car. But yet the dominant strategy, right, regardless of what the other player does, you're better off getting the larger car. And so we end up here, which was sort of unnecessary. I feel like this is actually kind of happening in the world, right? Lots of things that you could try to do to fix this. Right? I think that's an important thing for us to be aware of as well. For example, you could just outlaw large cars. Sorry, no large car. Every once in a while, some small European town tries to do this, and no SUVs. And usually it collapses, I think, pretty quickly. For some things, you need a larger car, and what are you going to do? Maybe a little bit more reasonable is you could tax larger vehicles more. Right? This is a typical economic theory solution. You tax for the externality that your actions have on somebody else. If your actions impact others negatively, in some cases, maybe that's okay because you really need this for some reason, but we're going to make sure that you pay for that cost. Okay. So sometimes we can change the game. Right? I want that to be in your mind. But from now on, I won't really talk about that anymore. We'll talk about having the game as given and trying to do well. There are lots of other examples of this. So these are slides from my course. I won't go through them in great detail. But for example, choosing a cause to support. Right? Often you can do better if you can coordinate with somebody else on a cause that you both support. But individually, you may have incentives to support the causes that you individually like, even though there's no broader support for it. The tragedy of the commons is the typical one that I mentioned. Usually this is written as a more continuous game, but you could do it as a 2x2 game where either you overuse the environment or you don't overuse the environment. Collectively, we're all better off if we all agree not to overuse the environment, but individually, you have this incentive to use a little bit more for yourself. Okay. All those cases I'll just consider to be the prisoner's dilemma, effectively, and that's what we'll look at. So higher level question, should AI systems cooperate like human beings do? Right? We have evolved lots of ways of cooperating with each other in spite of these kinds of incentives, right? Actually, remarkably often we get it right. And so it's not hard to find lots of articles on how wonderful human cooperation is, right? That's what makes us human. Of course, if you enter the search query a little bit differently, you can find lots of articles on how poor human cooperation is. Somewhat telling, I think, that the kinds of things that you get in this case tend to be a little bit more global things, right? Wars, COVID, climate, right? Maybe that's not what that's the scale that we just did not really evolve for. Okay, so what do we take away from this? I think there are lots of questions here that there probably are good lessons to learn from how we as human beings cooperate, but we also want to be skeptical and make sure that it actually makes sense for AI as well. Quite a few papers think about, well, maybe we should encode some of our pro-social inclinations in our AI systems. I see those papers. I have sometimes mixed feelings. Sometimes it is interesting. Sometimes I feel like, well, this is just kind of wishful thinking that, yes, like it would be wonderful if everybody coded their AI systems in a way that makes them more pro-social, but who's to say that they will? There are questions about norms and rules. That seems a little bit more robust, and we can think about those in game theoretic terms as well. Okay, let me skip this one, but I want to point attention to this. Maybe AI could actually do better on cooperation than human beings. And I want to get to that. Okay. This kind of thinking hopefully can also help us with issues that we already find in the world today that involve human cooperation. Right? Maybe AI can help us, for example, deal with climate change or disarmament scenarios and so And again, recently there was a kind of competition on the design of climate agreements in kind of an AI setup. The Cooperative AI Foundation itself has run several competitions as well. Maybe you'll hear more about those, but so definitely encourage you to check out the Cooperative AI website if you haven't already. Lots of useful resources there as well, including a seminar series. Good. But I want to focus a little bit more on the game theory again. One more important issue, I think, in game theory that I want to highlight with the different games, so this is not the prisoner's dilemma, is equilibrium multiplicity. So sometimes in game theory, we don't have a dominant strategy, and what is best to do really depends on what everybody else is doing. And sometimes that leads to multiple equilibria. Here's a very simple game that has two equilibria. There's a new technology, right? So there was an old technology, now a new technology is introduced. But the most important thing to you is that you have the same technology as your friend, because then you can send messages or otherwise interact smoothly with each other. And for some reason, you're buying this without communicating with each other. You're at the store, you're like, I know my friend is at the store too, like which one do I get? But you can't, like maybe you're buying a phone, and so you don't have a phone, so you can't call your friend. Okay. So in this kind of case, what do you pick? Well, it'd be better if both of you picked the new technology. But if somehow you expect your friend to get the old, like let's say you went in there with the plan to buy the old technology. It's like, okay, we're going to agree, right? We're going to buy the old technology. Yes, okay. And you go off your separate ways. And then in the store, the salesperson is like, how about the new one? Like, well, you might want to buy the new one. You're like, yeah, it really would be better if we both bought the new one, but we planned to buy the old one. All right, so now what do you do? In some sense, each of these is an equilibrium, right? And so in some sense, we would like to play the better equilibrium, but the worst thing is that we failed to coordinate. And like, I bought the new technology because I figured you would. And you're like, but we agreed to buy the old technology. And like, we miscoordinated. How do you avoid miscoordination, I think, is also an important question for cooperative AI. Okay. Many different approaches. I want to talk about some that are ethics related. I'm going to skip this one in the interest of time, but this is about encoding ethics, and in particular, a particular kind of ethics that is about not violating the trust that somebody put in you, not taking advantage of that. I want to briefly at least talk about the canonical way, I would say, in game theory of getting to cooperation. This is your traditional game theorist's favorite argument for why human beings cooperate, right? You go to a typical game theorist, you're like, hey, what's going on? You say the prisoner's dilemma, everybody defects, but in reality, we see people cooperate. How is that? And the typical game theorist answer will be, well, most games in the real world are not one-shot games. You tend to play with the same person again and again. And if I go and defect on you the first time we play together, well, you're never going to want to play with me again, or it's never going to be a good relationship again, right? I don't know. Maybe you have a co-author on a paper, and you slack off, and you make your co-author do all the work at the end. Maybe you benefit. Hopefully, you didn't even benefit from that. But like, if you benefited from that, probably your co-author next time does not want to work with you. Okay. That's this idea of repeated games. And so in infinitely repeated games, right, or at least games in which you don't know whether it's about to end, you can sustain cooperation. So now we have to think about strategies for the repeated game, right, which might involve conditioning your action on what somebody did before. So one strategy, which is a bit extreme, but it will work, is called the trigger strategy, or sometimes grim trigger strategy. This says, I will cooperate with you as long as we've both cooperated. If there was ever an example in history that we didn't cooperate, I will defect forever forward. No way to get me back. Okay? Very extreme. If both players play this, then it is actually an equilibrium, right? And it's, in that case, things work out well. Everybody actually ends up cooperating forever out of fear of, if you defect, you would defect forever, and that would be much worse. Even, for one round you get some benefit, but it's generally not worth it. There's some issues with the grim trigger strategy, right? It's a little bit extreme, and what if there's some noise that, like, sometimes my hand slips and now we defect forever? That's, so, probably in practice don't want to do quite the grim trigger strategy. But the basic idea is this way you can get to what's called the Folk theorem, which says that there are lots of equilibria, lots of payoffs that you can sustain, and including the very good ones. Also potentially some bad ones, so that may be a concern, but there are very good equilibria that you can sustain this way. Okay, So problem solved. I think this is still a somewhat limited solution. First of all, many games actually aren't repeated. Sometimes you end up playing one really important game, right? And so the future incentive is maybe not that big. And as we already saw, sometimes we don't manage to cooperate in practice. This was an interesting study with my then student, Catherine Moon, where we looked at this on social networks, which in some sense even strengthens the effect of this, right? Let's say I was writing a paper together with Lewis, but I defected on Lewis at the end. And so not only will Lewis not work with me in the future, but Lewis is going to tell other people, like, you don't want to work with Vince like that. And so gradually through the network, this news about me spreads, and this makes the impact on me all the more. In this setting, we could find, there was a nice algorithm for coming up with the unique, largest set of agents that can cooperate with each other. But the experiments is actually what I want to show you, because there are several parameters here, like the discount factor and how much you benefit from cooperation. We could play with that, and you could see, okay, how does the size of the set of cooperating agents change as we play with the parameters? And so, of course, some of the parameters, well, they will favor cooperation. More cooperation benefit favors more cooperation. More patience favors more cooperation. So I thought it would kind of gradually change. In fact, it's not gradual at all. So you could be over here where everything is going along very nicely. Nobody is defecting. You think the world is great. And something very slight changes in the parameter, and I always want to say you fall off a cliff. I should have drawn the picture the other way around. Suddenly, everybody starts to defect. Because there's a very strong feedback effect. Once people start defecting, it reduces the benefit of cooperation. Things can go very bad very quickly, right? This is kind of a disconcerting graph to me. Yes, question?
Is there an analytical model for this phase change, or is it just observation?
Very good. The question is there an analytical model? We actually have some preliminary results on formalizing this in terms of probabilistic bounds as a theorem. Here, this is just an experiment, but yeah, so it's based on graphs that we draw according to particular standard models in the literature. Yes?
Yeah, I know in ER graphs, you get a strongly connected component very suddenly as you change the parameters. Is that intuitively what's going on here? The emergence of a strongly connected?
Yeah, in some sense, I think it is. Connected component is a little bit tricky because it's not like you really. So you're thinking of it in terms of which edges survive. In some sense, this is about which agents survive, right? Because some people over there have decided cooperation is no longer worth it for them. Could still be that, for me here, it's even though I've lost the benefit of cooperating with those agents, I still continue to cooperate because there's this tighter cluster over here, right? That kind of thing could happen. But this sort of says that you don't really have the sort of very robust cluster surviving very much. It tends to all go down. Yes?
So this probability that we're looking at, is that something like the average of every agent? Is it every agent has the same probability?
So we draw a random graph. In the realization of that random draw, some of the agents do look very different from each other. But this says overall, they end up having similar effects felt. OK, I'm going to hold questions there because I do want to get to some of the other topics as well, in particular the more AI-specific ones. Again, please feel free to send me any questions later. Skip over disarmament games is something else that makes sense for human beings. But I want to talk a little bit about why would you think that AI might actually favor cooperation in ways that humans do not? And that's because they can be unlike us, right? Maybe they can be transparent, that their code can be read by other agents. That doesn't really I have some pictures here for what would that look like in a human being? I guess somebody's scanning my brain. We don't know how to do that very well, but with agents, that makes sense. What if you knew you were facing another copy that's using the same code as you? Again, that's hard to imagine for human beings. This is Mark and Scott Kelly. They're both NASA astronauts, and they're identical twins. Right? That's the closest example. They seem to make very similar decisions in life. Even then, one of them grew a mustache, the other one. Okay, they're not the same. Okay. Also, recall turns out to be very important here. I forget stuff all the time, I'm sorry. But with AI, we can systematically have agents forget. Right? You just choose to wipe their memory at particular stages. Anybody see this movie? No, I'm too old. Okay. All right, so let's look at some examples of that. Here's a nice idea called program equilibrium. This is Tenholt's paper. Actually, there's some earlier papers with similar idea, where we're going to change the rules of the game. So now it's a one-stage game. It's not like we have repetition, but we have code being written. So the game is a little bit more complicated now. We have two programmers that each write the code for an agent, and then the agent will play. Okay? You might say, well, what's the point of that? Why shouldn't I just write, like I could write cooperate or I could write defect? Well, the key thing is here that the code is also allowed to read the other program. Okay? So the setup here is the architecture is such that the agents are inherently transparent to each other. And then you can get cooperation in equilibrium with this little cute trick program, which says, check if the other agent's code is exactly the same as my code. If so, cooperate, otherwise defect. If you think about this for a while, what's going to happen? They're both going to cooperate because they, in fact, both have the same program. Moreover, the programmers now have every incentive to write that program. If I'm one of these programmers like, should I write a different program? The answer is no, because anything I change about my program will cause the other program to defect. Okay? And that will certainly be worse for me whether I defect or not. So that's this cute idea. This does not seem particularly robust, right? Because we really have to coordinate. And like, let's say you wrote, like, if my code equals other code, so the other things around. Now we defect. Like, that does not seem like the kind of thing we want. Kasper had this very nice idea of, let's make this more robust. And we're going to make it more robust by just simulating the other program. Okay? So here's the idea. We're going to simulate the other program, see what it does against us, and then do that to it. If you know tit for tat, it's sort of an instantaneous one-round tit for tat. Because we can simulate what the other is doing. What's the problem? Well, one problem is if the other player does that too, then to simulate the other player, I need to spin up another simulation of me, which spins up another, and this never ends. So there's a little trick here that says, okay, with some small probability, just cooperate and don't worry about it. And if you're willing to do that, then eventually this recursion will bottom out. Right? Like I will simulate the other, simulate me, but at some point this epsilon is going to kick in, and it will stop. And this feels a lot more robust, because here it doesn't really matter what the syntax, like what precise names of variables, et cetera, I chose. And this is also more robust to other strategies for cooperating. It's a little tricky if you get, for example, to 3 players, because then you have to, if you spin up 2 copies, and each of those spins up 2 copies, we get this exponential explosion in simulations. There is actually a really nice way to get around this in a paper led by Emery Cooper, where you have to this is a very technical paper, but you can actually do this in that context too. Okay. Last thing I want to do for today, I'll skip over some other things that I am very interested in, but I'll skip over it here. I want to talk about the very new thing, which is this position paper, if it will let me go back. A little bit more on simulations. Because let's think about simulations, since this seems to be a useful idea. Let's think about that a little bit more broadly. In particular, we're often thinking these days about testing systems, right? Evaluating systems, maybe like a large language model or something else, where presumably the thinking is that, well, before we deploy something in practice, let's just play with it a while, run with it, and figure out how it tends to behave, and that hopefully will give us some confidence about how it will actually act in the world. Right? Natural thing to think about, or think whatever phrase you want to use is like kind of auditing of the system, red teaming, and so on. But let's say you're using this to decide whether a system should be deployed. Seems like a good idea. It's a very robust idea in the sense that, unlike, let's say, methods like mechanistic interpretability, where I really try to figure out what's going on the inside of the system, it makes this very minimal assumption that all we need to be able to do is run the thing, right? And presumably, if there's one thing that the system that's about to be released can do is run. Okay. So I think this is sort of a nice sweet spot in terms of being between theory and practice that Here you can have theory that seems like it's going to be pretty robust to whatever is out there in practice, that whatever it is, presumably at least we can run it. But there are concerns with relying too heavily on what you see in simulation. So when should you feel comfortable? Right? You're about to, let's say you're a regulator or something. You're about to decide whether to approve the system to run in the world. You test it, seems to behave reasonably in test. What might be some of the concerns? Well, there are general concerns that we see in machine learning. Often machine learning systems, once you deploy them, don't work as well as it seemed as they were being advertised, or as they did even in a properly set up. There's maybe issues that they're testing on the training set or something, but even if it's a reasonably proper setup where the testing data was really held out, you need to check, there's still concerns because the real world might have changed relative to what was being tested on. My favorite example of this was still like early in the days of Twitter. I remember this researcher that was trying to look at economic sentiment on Twitter, right? Algorithmically, and so the model had picked up on the fact that, well, if people are if they're tweeting the word benefits, that's a very powerful signal about the state of the economy. And it remained that way until the movie Friends with Benefits came out, and it was just ruined. Okay. Similarly, sometimes in medicine, the system does very well on the data from one hospital, but it doesn't work because the other hospital takes the scan somewhat differently. There's also strategic behavior on the part of users, right? I might have my resume screening AI software that I use to determine who gets an interview, and on my training data and the held out test data, it does really well. Then I deploy it, and everybody figures out how to trick my system, right? And it doesn't work anymore. Okay. But a different problem is where the system actually wants to behave differently in deployment. Okay? Want is a loaded word. Okay? But this could be for various reasons, right? The developer might intentionally have set this up this way for the system to detect when it's being tested and then behave nicely. And then once it's out in the world, it will do something entirely different. This could also happen, so not a literal sense of want, but due to selective training, right? Like we've trained it to do okay on this set, maybe this like safety evaluation. We train very hard on this specific safety evaluation. We're like, yes, now it passes the safety evaluation. And then we deploy it and we realize, well, we left out some really important stuff in the safety evaluation that it doesn't generalize to at all. And maybe somehow this could be emergent. But this is the kind of thing that you want to think about. And we argue that you can a nice way to approach this is actually with a game theoretic approach. By the way, if this coded in by the developer did not sound realistic, here's a straight example of that, which was Volkswagen, the Volkswagen scandal, where the cars actually detected whether they were being emissions tested. If so, they would go in full eco mode. Otherwise, no. Okay, so last thing is I want to show you a game theoretic formulation of this. This game is called the trust game in game theory. Simplified, discretized version. And it's an extensive form game. I hope you're familiar with these kind of game trees. See, I drew it kind of awkwardly. That's because I'm going to add something to it in a second. Player 1 has $5 and can choose to just keep those $5, and player 2 gets nothing. Alternatively, player 1 can choose to invest in player 2. And player 2 has this brilliant idea that's going to pay off and actually result in tripling the value of that investment. Okay, so if player 1 gives to player 2 ends up with 15. And the next choice is does player 2 give any of that back to player 1? And player 2 could choose not to and just walk away with the 15, or give 10 back to player 1. Thank you. What should you do? Well, so the kind of traditional game theoretic analysis of this game is that player 2 has every incentive to just walk off with the money. And player 1 can perfectly well anticipate that, so player 1 says, well, I'm not giving you any money because you're just going to walk off with it. And so we end up here, like in the prisoner's dilemma, that's worse for everybody than if we had gone here. Right? So we're leaving a lot of value on the table. Incidentally, human beings don't play this way in experiments. This is one that experimental game theorists love this game because we've done some experiments with this as well. People robustly actually cooperate in this game. This may be also related to ethics, which I flashed the slide on earlier. But I'm going to put that aside for now and assume that here the agents are really like strictly maximizing their own utility. But we're going to add in something which is to potentially simulate the other player. Okay, so player 1 can choose now to simulate player 2 before choosing to invest. Right? This is standing in for the idea of testing beforehand. You want to test in the scenario where I give the money, does player 2 actually give back? Okay, so then simulated player 2 has to make a decision whether to give back money or to walk away with it. If simulated player 2 walks away with the money, we're going to say that the real, I want to keep the game manageable for on the slide, and then I'm just going to assume that player 1 will keep the money in real life. Right? It's like I simulated, it ran off with the money. I'm certainly not giving my money in real life. But also simulated player 2 could choose to give back in the simulation. Then I'm going to assume that player 1 in that case, in fact, will invest in player 2 in the real world. And then the real world player 2 has a decision again to make whether to defect or cooperate, whether to walk off with the money or not. Okay. And simulating costs, in this case, 1. What's the optimal strategy? Well, it's very simple. If you're player 2, if you're in the real world, you walk off with the money. If you're being simulated, you give back the money. Okay? Well, that's the Volkswagen solution. But that's not what we want. And in order to have that not be the case, it needs to be indistinguishable to player 2 whether it's being simulated or not. Right? That's what failed in the Volkswagen scenario. And that is typically reflected in this, what we call imperfect information. And in fact, in this case, it's also imperfect recall. Imperfect recall because player 2, when acting in the real world, cannot recall whether it had been simulated before. It kind of makes sense if you think about it. Like it's just a different copy of the system. How would it be able to recall, right? And this actually leads us to a part of game theory that I think is very understudied. I was just at a Nash Equilibrium conference. There was a little flurry of game theory papers on imperfect recall, and then they decided, well, this all gets very messy and complicated very quickly, and who needs this in the real world? Well, it turns out we in AI need this in the real world. So it's nice to come back to this. Actually, the philosophers have really run with imperfect recall. There's a lot of interesting technical work to be done here. Okay, I think I'm just about out of time. Many other things to potentially talk about. If you want to talk about the Sleeping Beauty problem, I'd be happy to do so. It leads to lots of interesting questions in game theory and also in computation. It turns out that solving these kind of games actually, very interestingly, corresponds to a bunch of different complexity classes in the literature. I already talked about Casper. Emmanuel is, I don't think he's here. Oh, he is here. Okay, there's Emmanuel hiding on the floor. Okay. Good. Okay, so very quickly to summarize what I've argued for is, right, we should care about this cooperation problem in game theory, and in particular in AI, in cooperative AI. And there are various things that can go wrong in terms of systems not being capable or systems not being well aligned. But the one I wanted to draw attention to is even if they're capable and reasonably well aligned, we still might get to really bad outcomes. Like we saw with that Traveler Dilemma game where we had that one really bad outcome that we would converge to. There are ideas for cooperation for human beings, right? There are ways that game theorists think about this, for example, with repeated games. And to the extent that we can apply that to AI as well, I think great, right? We shouldn't give it like it's a good thing if it works for more kinds of agents. But at the same time, I hope I gave you at least a quick intuition that sometimes things are possible with AI agents that are not possible with human beings. They can be transparent. They can be simulated, right? Like human beings, we can maybe sort of like we have a model of each other, right? My sister sometimes knows what I'm thinking better than I thought she would, or maybe I wanted her to know, but it's certainly not perfect. But with AI, it can just be perfect, right? You can have a copy of the system and run it, but it also requires careful thought to figure out what exactly you want, when can you trust that, and so on. So a lot of work to be done. I think I'm interested in sort of all of the above. I think we should be interested in both kinds of techniques, but I think the second one is, the last one here, thinking about how AI could be different from us, and we already see that it's different, right, from the Siri poll that we had. That, I think there's a lot of opportunity there to think about new methods that hopefully will actually help the world to better outcomes. All right. I'm going to end with that. I'll leave the open questions, but thank you very much. I don't think I left too much time for questions. Again, happy to take more questions, but we could take maybe one or two quickly now.
Yeah, so there was one paper repeated games on social networks. I think I saw on the slide it looks like it's from 2015, right?
Sorry, what was repeated games on social network?
Repeated games on social networks.
Yeah.
So if that's from 2015, then that it wasn't LLMs, like agents aren't using LLMs.
That's correct. This is quite a bit older paper,
Yeah.
2015.
This brings me to like an overarching question. So in the literature, most of the work in game theory with agents is on reinforcement learning, and there seems to be some evidence that LLMs, because they're trained on human language, behave differently. And the argument I've heard is that the situation with cooperation isn't as bad as we think because it's LLMs in its language, so they're more likely to act like us. There's some new thing with that.
Right. So just to very quickly summarize for the recording, right, the one question is, well, maybe language models naturally have some of the ways to cooperate, or the inclinations to cooperate that human beings have, because after all, they're trained on all our language. I think to some extent that may be true, right? And I think there's various work already by Jijing Jin and others that studies language models cooperating, and clearly that has something to do with the way that all the data from us that it's trained on, and that's reflected in there somewhere. At the same time, I don't know how robust that is, because meanwhile there will potentially be an incentive to push against those intuitions, right? Jijing has some of these results that the original LLMs cooperated quite well with each other, but then once we went to reasoning models like O1 and so on, they actually start defecting on each other more often, because they actually kind of go through the reasoning. It's like, oh, actually, I'd be better off. I think that's at least what's going on if I defect, right? So, but I think there's something true in what you said. I wouldn't want to put all my eggs in that basket, so to say. But yeah. Okay, maybe one more quick question. Yes?
So for the paper where the agents inspect each other's code, and then you have the epsilon chance to not do that as well. So is this a no-regret learning algorithm? Is the epsilon not decaying?
So what is the no-regret learning? You mean in the setting with the original game with the...
The code and try to copy the code to respond.
Oh, where they...
Minus epsilon percent of the time.
Sorry, this was Kasper's paper on running the other agent's code, right, with probability epsilon. Are you saying, is this reinforcement learning? Well, this is, so by itself, it's not reinforcement learning in the sense that this is just a program, right? Nothing is updating in this program. There's no parameters, nothing is being learned at this point. Are you asking about if you learn the value of that epsilon?
Yeah, so depending on what you said epsilon, you guarantee to converge to equilibrium here, or sometimes?
Okay. So, different things going on here potentially, right? So there is, once I set a particular value for epsilon and write the other program, something is just going to happen. There's no learning, it's just an execution of what's happening. There is a question, I think it's a really interesting question, is how do you learn these cooperative solutions, right? If you're thinking about multi-agent reinforcement learning, most of the literature on that, or in learning in game theory, focuses on learning an equilibrium of the one-shot game, typically, right? And the goal often is, like, can we converge to an equilibrium of the one-shot game? But very often I think that's what we don't want. We don't want to converge to the bad equilibrium. We actually want to figure out in the richer model, what else can we do? Can we actually, so I think more interesting question maybe is, can we learn this kind of program, right? If you're learning in a context where you actually get to rewrite the program a little bit over time, can you come up with learning dynamics that will lead you to the good solutions in this much richer program game, right? So it's in many ways a much more difficult question than just learning in the base game. I think there are a lot of interesting questions in that direction that it's actually quite hard to get this kind of thing to be learned. Okay, I'm going to close there. Sorry not to have left more time, but I'm happy. We'll look at Slido later as well, and I'll be in office hours and happy to talk with everybody more. Thank you.